Hey class, welcome back. My name is Payam Hojat. This is Module 3 of CCNA Networking Fundamentals. Today we're going to be talking about protocols and models. This module specifically is going to be an overview of the basics and fundamentals of networking. How does one device talk to another? What are the rules? What are the protocols? What are the models that are being used? More specifically, we're also going to be talking about encapsulation and data access. Okay, so let's go ahead and jump into the first part, the rules. 3.1. Okay, so whenever a device wants to talk to another device on a network, we have a source and we have a destination. The source is the sender, the destination is the receiver. And that medium, that media or that vehicle that the message is traveling through to get from point A to point B, that's called the channel. All right. So point A, the sender, we usually say the source, will send a message through a channel or a medium to the destination or the receiver. Okay. Now, in networking, we usually say source and destination more so than sender and receiver. So make sure you understand when we say source destination, that's where the message is coming from. That's where the communication is originating from. And the destination is like its end goal, its end point. Now, protocols from a sender to be able to send it to a receiver, a source and a destination to be able to communicate to one another, right? There has to be some governing rules, right? I can't speak Italian when the destination or the receiver can only speak English, right? I can try to communicate as much as I want, but they're not going to understand it. So there has to be some governing rules. There has to be some certain protocols in place so that point A and point B, the destination and the source and destination, can speak on the same language, on the same medium, on the same protocols, so they can mutually understand one another. Okay? These protocols are specific to the type of communication method being used. In addition to that, the medium or how that message is going to be communicated is just as important. So if you're trying to talk to someone else, if you're trying to send a message to someone else, all right, how are you going to send that message to them? Via voice? Are you going to write a message or note to them? Are you going to sign to them? So there's different mediums of how you can send that message. And then within each one of those mediums, there's different languages that you can utilize. For example, when you speak, you can either speak Italian, French, English, right? Or even writing, right? Which language are you using? Are you writing? Are you writing in Arabic? Are you writing in Spanish, etc.? Right? So those protocols, those governing rules are really important for the sender and the receiver to be able to communicate together properly. Okay? So if we're going to be talking about the signal, all right? The signal is the how. All right? The message from the sender, how am I going to send it to the destination? The how is called the transmitter. So that would be more so along whether you're going to say it orally, are you going to write it, the message? Are you going to sign the language? That kind of structure. Okay? Now, in addition to that, there needs to be rules established on how individuals are communicating to one another. For example, you've decided the medium, you decided the language. Now, there's an additional level to that in terms of what kind of grammar you're using, how fast you're speaking. Are you going to send acknowledgments? Yes, I understood what you said. Let me just confirm that, like sending it back to you. So there's additional rules to make sure that the communication is understood by both parties. Okay? So there's an additional layer to that. Now, network protocol requirements. The protocols that are used in network communications share many of these fundamental traits. We were just using analogies, right? So in the networking world, we use message encoding, formatting and encapsulation, message size, timing, and delivery options. So everything we were talking about before is just an analogy, right? I'm talking to another person. How am I going to communicate to them? Now, from a device-to-device standpoint, we use these 5: encoding, formatting, encapsulation, size, timing, etc., to be able to create those protocols, those rules of engagement. Now, message encoding, it's one of the first steps of sending a message. Encoding is a process of converting information into another acceptable form. It's like formatting, okay? Getting it ready for transmission. And then the sender or the source usually encodes that message. But at the same time, the destination will also have a decoder on its side to decode and reverse the process to be able to interpret the information. Okay? So here's an analogy that they use. Imagine a person calls a friend to discuss the details of a beautiful sunset. To communicate the message, she converts her thoughts into an agreed upon language, let's just say English. She then speaks the words using the sounds and inflections of the spoken language, right, that convey the message. Her friend listens to the description and decodes that sound to understand the message he received into his brain, right? So the decoder is the ears, and that goes to the brain for the destination. But the sender, she's decoding it or encoding it with her mouth because she's saying those words. Okay? Now, message formatting and encapsulation. When a message is sent from the source to destination, it must use special format or structure. Message formats depend on the type of message and the channel that is used to deliver the message. Now, a common example that a lot of people use is when you want to send mail. So a common example of requiring the correct format in human communications is when sending a letter. So an envelope has the address of the sender and receiver, right? The sender is on the top left-hand side. The middle of the envelope is going to be the recipient, the person, the destination where you're receiving it. If the destination address and formatting are not correct, the letter is not delivered pretty much, right? You have to have the name, you have the address, then you have to have the city, state, and zip code, right? If you don't put it in that format, it's not going to be sent, right? And then you can't communicate to the destination. The process of placing one message format inside another message is the encapsulation method, right? So the envelope has a source and destination, right? The sender, which is you, hypothetically, where you came from, right? And your street address. And then the destination is the person you're sending that letter to and their physical address, which is their street address as well. But there's no data necessarily. Your message is not really being sent on the letter. There's something inside the letter or envelope. That content that's inside the envelope, that's the message that's being sent. And because you're putting content inside that envelope, that's called encapsulation, right? You have the message, and then you encapsulate the message with overhead with the source and destination addresses. All right. Now, the message size is really important for interpretation and understanding. When people communicate with one another, the messages that they send are actually really broken into smaller parts or sentences, right? You're saying a story, but the story is comprised of a bunch of sentences. That's kind of how networking works, right? So you want to send some type of message to someone, but it's not all going to be sent at once. It's going to be broken up into smaller parts, smaller, easily digestible parts over the network. Just like how a story is, right? Your story has sentences. And these sentences are limited in size to what the receiving person can process at one time. It makes it easier for the receiver to read and comprehend that specific message, essay, story that you're trying to tell. Now, message timing. Message timing is also very important in networking communications. There's flow control, response timeout, and access method. So flow control is a process of managing the rate of data transmission, how fast you're talking. Response timeout is if a person asks a question and does not hear a response back within an acceptable time, the person assumes that there's no answer, right? So you're calling someone, right? And you ask them something, but they don't respond. Maybe there's an error or the call got dropped, right? Because they can't hear anything. They're not just going to stand on the phone for 3 hours hoping to see if you respond back. After a minute or two, when they don't hear your voice, they're going to hang up, right? Otherwise, they're going to be on the phone forever, and there's no point because there's no communication back. You're not on the other line. Your call got dropped, right? So there has to be a specific timeout. Okay, after a minute, I didn't hear back, I'm going to hang up the phone, right? And then there's access method. This determines when someone can send a message. So now access method. So the access method determines when someone can send a message. This is specifically important for collisions. So devices can't talk at the same time usually because then a collision will happen. Just like how if you're talking to your friend and if both of you talk at the same time, you're not going to be able to understand each other. You have to wait for your friend to first finish their thoughts. Once they pause, then it gives you a signal that, okay, I can now speak because he's not saying anything, and if I speak, he's able to understand and interpret it. Now, from a device and networking perspective, if two devices are trying to talk to one another, it's just going to cause an error and they're going to clash into each other, kind of, right? So access method is who gets to talk first, right? Okay, there's rules of engagement. Once you take a pause, all right, then I can start speaking, right? Message delivery options. A message can be delivered in multiple ways. Unicast, multicast, or broadcast. Unicast is one-on-one, you're talking to only your single friend. Multicast is when you're talking to multiple people, multiple selected people, right? So pretend you have a classroom, okay? A classroom, the teacher will talk to an individual student, have a one-on-one meeting. That's called unicast. Multicast is a select number of individuals, all right? So it'll say, pretend the class is broken up to 4 groups, group A, B, and C, and D. Multicast is the teacher is only going to talk to groups A, okay? She has a specific message for only group A because they were causing havoc. They were not doing their work. She has to go talk to them. Hey, get on track, finish your assignment. All right. But groups B and C and D, they're fine. The rest of the class is doing fine. but they don't need to hear that message that, hey, get back to work. Only group A needs to, because they're the ones who's slacking off. And that's kind of what multicast is, right? There's multiple people that she's talking to, but it's in kind of like a group. Now, broadcast is like talking to the whole class, everyone, okay? That includes all the groups, A, B, C, and D, and every individual within each of one of those groups, okay? Unicast is one-on-one. Multicast is select individuals inside of a group, and then broadcast is to everyone. So here, multicast, see individuals, and then broadcast to everyone. And here's more of a visual for y'all. Unicast, source directly talking to one person. Multicast, talking to selected number of people. Broadcast to everyone. Okay. Now let's go into 3.2, Network Protocol Overview. So in network protocols, there's different types of protocol types. There's network communication protocols, network security protocols, routing protocols, security discovery protocols. These rules, these protocols, they have many functions in a network. Network protocols pretty much define a common format and set of rules for exchanging messages between devices. Protocols are implemented by end devices and intermediary devices in software, hardware, or both. Each network protocol has its own function, format, and rules of communication. Okay? So, networking protocols specifically are, for example, TCP, HTTP, which is more on application level, IP. Network security protocols are SSH, which is secure shell, secure sockets layer, TLS, which is transport layer security. Protocol specifically for security stuff. Routing is protocols of how routing works. There's BGP, OSPF, RIP, IEGP, and then service discovery protocols, which is DHCP, DNS. All these, I know these don't sound like anything to you right now, but as we go on through the rest of the course, these are all specific protocols that you will utilize, you will leverage, you will implement in your assignments down the road, especially in networking. For example, DHCP, how you connect to a Wi-Fi and automatically get an IP address assigned to you. That specific protocol of getting that IP address assigned to you, reaching out saying, I want an IP address, and having the routers assign you a specific IP address, that's using DHCP. Now, DNS specifically, how you type in a web address, you want to type in google.com, how it translates that into an IP address, and the methodology, it goes from one server to another server to another server to be able to find that specific web page for Google and have that come back. That's called DNS, right? Usually you have DNS servers that already has that translation of where to exactly go to pull that web page, but that's for another discussion. Now, network protocol functions. Computers and network devices use agreed upon protocols to communicate. The table lists the functions of these protocols. So for addressing, we either use Ethernet, IPv4, IPv6. Now, these protocols specifically, they're not all the same type of protocols. For example, IPv4, IPv6 works on the network layer. Ethernet works on the data link layer, which is layer 2 versus layer 3 for the IPs. Reliability, we use TCP. Flow control, we use TCP, provides flow control as well. On layer 4, sequencing, same. Error detection. Various protocols that provide error detection. Ethernet, TCP. So layers 2 and 4 are usually the most predominant ones, but there is some error checking at the IP layer as well. And then the application layer includes the closest to what the end user sees, like me able to interpret that network communication, that device, that message. That's like the web pages, right? HTTP and HTTPS, right? That also includes DHCP, DNS, and other protocols that we'll talk about down the road. Protocol interaction. So a message is sent over a computer network typically requires the use of several protocols, right? As we listed up here, we talked about Ethernet, we talked about TCP, we talked about HTTP, HTTPS. These are all on the different layers, right? And all of them can be used. No, you can't use all of them, right? You can't use they'll be different, but sometimes you can encapsulate IPv4 within IPv6, but that's a different story. But you have to use multiple, right? At the layer 2 level, you have to use Ethernet, right? That's one protocol. And then at the layer 3, we have to use one of the IP protocols, right? Let's just say IPv4 for the sake of argument. And then at the application layer, we have to then choose what are we using? Are we using HTTP or HTTPS, right? So there's like a stack develops, right? Like you can see here. You have the Ethernet, then you have the IP, then you have the TCP, then you have the HTTP, right? Now, protocol suites. Let's jump into 3.3. In many cases, protocols must be able to work with other protocols. A protocol suite is a group of interrelated protocols necessary to perform a communication function. One of the best ways to visualize how the protocols within a suite interact, to view the interaction as a stack, right? We're talking about a stack. That's what you hear. A protocol stack shows how the individual protocols within a suite are implemented. The protocols are viewed in terms of layers, which each higher level service depending on the functionality defined by the protocols shown in the lower levels. The lower layers of the stack are concerned with moving data over the network and providing services to upper layers, which are focused on the content of the message being sent. Okay? So if we go back here, down here, this is technically, we can conceptually think of this as a stack, right? Ethernet, IP, more so of how that communication is being sent, and then this TCP, HTTP, specifically the HTTP is how that communication is being delivered to the end user. All right. Now, a protocol suite is a set of protocols that work together to provide the comprehensive network communication services. This has been going on for ever since the 1970s. During the evolution of networking communications in the internet, there were several competing protocols. We had the TCP/IP, ISO, AppleTalk, Novell. TCP/IP is probably the most relevant one and the one that's still being used today for the most part. For the sake of this class, that's what you're going to focus on. Okay. Now, the TCP/IP protocol are available for the application, transport, and internet layers. There are no TCP/IP protocols in the network access layer. The most common network access layer LAN protocols are Ethernet and wireless local area network protocols. Network access layer protocols are responsible for delivering the IP packet over the physical medium. Okay? So network access layer, even though it says Ethernet, it also includes layer 1, which is the physical medium as well. All right, so it kind of combined layers 1 and 2 of the OSI model. the figure shows an example of TCP IP protocols used to send packets between the web browser and the web server. Okay. HTTP, TCP, and IP are the TCP IP protocols used. At the network access layer, Ethernet is used in the example. However, this could also be wireless standards such as wireless local area network or cellular service. Okay. Now, today that TCP IP protocol suite includes many protocols and continues to evolve. So within each of these layers, the application, transport, internet, network access layer, there's different types of protocols that can be used. It's not always going to be DNS. It's not always going to be TCP. It's not always going to be IPv4. So over the years, there's different protocols that are developed and kind of like put into the layers that can be utilized. For example, we created IPv6 because we were running out of IPv4 addresses. So we snuck that in there, you know? And I'm not going to read through every single one of these specific protocols. Highly recommend everyone reviews them on their own. But these are some of the more prevalent ones that we're going to be using over the next, throughout the semester. Includes DHCP, which is how you get your IPv4 address when you're NATing. POP, IMAP, and SMTP are all email protocols. File transfer includes FTP, and then the secure version is SFTP, and then trivial is still FTP, that's connectionless, and then web services is HTTP, HTTPS, REST. Okay. Now, going into the TCP/IP communication process, very briefly, I'll touch on encapsulation because it looks like that's what they're talking about here. But there's a whole nother section we'll go into in a little bit. But you'll see here your data is this little segment. And then to add on to the layers of protocols that we're talking about here, the application protocols, the transport protocols, the internet layer protocols, what happens is we take the data, the message that you want to send, and then we append the protocols to that message. For example, the TCP, right? You have the application layer, and then you have the transport layer. For example, you take the transport layer protocols, you append it to the message. And then when you go down the stack, you then put the internet layer protocols, you append it to the transport layer protocols. And then you can still go down the stack, you go to network layer access, then you put the network access layer protocols and you append it to the internet layer. So it kind of builds upon one another. As you can see here, you have your data, and then you create this TCP segment, or we call them PDUs. You take your data, and then you append the TCP protocols, and then you append your IP protocols, and then you append your Ethernet protocols. And the Ethernet frame specifically, there's a little overhead at the end of the message to kind of close it up together. But I think this quick visual will kind of make more sense. So you have your data, your web page that you're going to, usually HTTP, that's your data. And then you encapsulate it, right? You add the TCP protocols, you append it, and then you encapsulate it again. You're adding your IP protocols, and then you're adding the Ethernet frame, which is additional overhead in the beginning and at the end, right? That gets translated into binary. You send it over to the web client, and the web client receives it, right? And once a web client receives it, it actually decapsulates it in the very exact opposite. So I think maybe this one has it. Yeah. So what happens here is it decapsulates it. It removes the Ethernet. It reads the Ethernet here. It reads the Ethernet frame. It understands what protocol is happening at the network access layer. okay, for interpretation. Once it reads it, it removes it, and then it looks at the IP protocols that's being used. Once it understands the IP protocols that's being used, it will strip the IP overhead off, and then it will read the TCP overhead, understand the protocols that's being used, strip it off, and then you have your data, right? And then the data is sent to and viewed by the user. That's pretty much what encapsulation is. It goes up the model and then goes back down the model. So that's just a brief overview. Now let's go into standards and organizations. I'm not going to spend too much time in standards and organizations. I'm actually going to jump down to here. There's a couple that you need to know. So standards and organizations pretty much define those protocols and what the protocols can and cannot be, approve what can be added, what can be removed, decommissioned, deprecated, etc. These are the four that are pretty prevalent right now in electronic and communication standards, more specifically the IEEE, Organization of Electrical Engineering and Electronics, dedicated to advancing technology, innovation, and creating standards in a wide area of industries, including power, energy, healthcare, telecoms. Important that IEEE networking standards includes 802.3 Ethernet, 802.11 wireless LAN standard. So IEEE is probably the most prevalent one that you will probably have to get a little more familiar with. The other ones, it's there, but not so much for the sake of the argument for this class. Now, reference models. Let's jump into reference models. All right. So the benefits of using layered model. We went over that network stacks of suites up here. Let's jump back here real quick. Come on, click. You see here how we have these different layers: application layer, transport layer, internet layer, network access layer, right? The benefit of having this layered approach is that whenever a new protocol comes in, it helps with the interoperability of different systems and devices, technologies, to be able to use the same protocols at the same time. So, you cannot actually watch real packets travel across a real network the way you can watch the components of a car being put together, assembly lines. So it helps to have a way of thinking about a network so that you can imagine what is happening. A model is useful in these situations. So, for example, whenever someone wants to create a new protocol, they understand the model that it goes through so they can actually help all networking devices go through like relatively the same model, layered model. So whenever someone wants to create a new protocol, they know that all networking devices use this model. So let me make sure that whatever I create works with the model, then it kind of ensure that all the networking devices can work properly with this protocol because it fits the model. It creates that framework, it creates that skeleton. Okay, so like I mentioned here, the benefits assisting in protocol design, because protocols that operate at a specific layer, which define information that they act upon, and a defined interface to the layers above and below, right? It fosters competition because products from different vendors can work together, preventing technology or capabilities from changing in one layer from affecting other layers above and below, and then providing a common language to describe networking functions and capabilities, right? We're not talking about Apple's networking model. We're not talking about Microsoft's networking model. They all use the same thing. So we can have Macs and Windows computers talk to one another, right? So it's good to have one model, and they can make protocols, utilize the model that we all use to be able to, like you see here, design better protocols that everyone can use, and to make sure that it works. The networking fundamentals works. Okay. Now we have two different types of models. We're going to be talking about the OSI model, which is probably the most prevalent one. It really breaks the layers down. And then we have the TCP/IP reference model, which kind of combines a few of the layers together. Previously, in the protocol suite that we were talking about earlier, it was using the TCP/IP model. But in addition to, you saw there's 4 layers: application, transport, internet, and then network access. In the OSI model, it actually breaks it into into 7 layers: the application layer, the presentation, the session, the transport, the network, data link, and then the physical. For this class specifically, we're going to be using the OSI model more so because we're going to understand and define each of these layers more in depth. Okay? The physical, right? What kind of physical medium is the device going? One device talking to another device, right? Is it hardwired? Is it wireless? Data link is where you do your switching. So whenever we're going to be configuring switches, we're going to be using the data link layer to communicate from one switch to another. It uses the Ethernet protocol. Networking is more so IPs. So that's when you want to talk from one network to another network, one router to another router in a sense. The transport layer helps with reliability. In addition, does some error checking as well. The session layer in the OSI model manages the session in terms of when to terminate, when to start that communication channel between the source and destination. Presentation just formats the data itself, the message that's being sent, into the application layer. And then the application layer is, for example, like the web pages that you see, and that's presenting to the end user. All these layers work in harmony between the layer above it and the layer below it. It cannot work if they are not in sync. The layers are not in sync. They won't be able to pass that information up or down the stack. Okay? And each one of these layers adds a level of overhead to the encapsulation process. So for example, when device A is sending something to device B, it will encapsulate and add protocols at each of these layers onto the message. And then once the receiver receives that specific message, the receiver will remove the layers of overhead from each of the from the packet itself, from the data that was sent, until it reaches the application layer with the data and present it to the end user. And we'll go into that in a little bit. So you see here, this is just a little table that kind of explains each of the layers here. Now, in contrast to the TCP/IP model, which is on this side, it kind of combines the application presentation and session layers together into one, and then it also combines the data link and physical layer into the network access layer. Okay, but pretty much it does the same things. It's just combining some of those layers together and smushing it. The functionality is identical in concept, so these 3 layers directly translate into the application layer, and these 2 layers directly translate into the network access layer of the TCP/IP model. The only difference is why, you may ask, why do we have both models? It's more so specifically the use of it. The OSI model is more theoretical. We use it for teaching, learning, troubleshooting, because it goes more detail of the TCP/IP model, and we can even break these layers down into further sublayers, especially the data link layer. And then the TCP/IP model, more so, it's a little more practical, real world use, right? We just combine them together. some of these together so it's more broad, right? High level in a way. Okay, so let's now go into the next section. Data encapsulation. All right. Okay, now going into segmenting. So, like I mentioned before earlier in this video, when we're communicating a message or we're saying a story, we break our story up into sentences. Why do we do that? It's just easier and more manageable, right? For us to communicate that story and for the end user or the receiver to be able to understand the story. It's easier to understand smaller sentences rather than one long run-on sentence, right? So a better approach to networking is we divide the data into smaller chunks, something easily more manageable to send over the network. And this is called segmenting. We take our data, we break it up, and that's what into segments, and then we send each individual segments over the network. Okay? Segmentation is a process of dividing a stream of data into smaller units for transmission over the network. Okay. Segmentation is necessary because data networks use TCP/IP protocol suite to send data in individual IP packets. Each packet is sent separately, similar to sending one long letter as a series of individual postcards. Packets containing segments for the same destination can be sent over different paths, which is really important as well. So, for example, from an efficiency standpoint, you have 3 paths that lead to your destination. So you can send, if you break your data message into 3 different sections, you can send each one of those segments over the network through 3 different paths, and it will get to that destination, and the destination will put those segments together to be able to read and comprehend that original story that you're trying to tell them. Okay? Now, when you break things up into different segments, you might wonder, what if they're sent in the wrong order? How would that work? How does the end user reassemble all those segments to be able to get the big concept or the story in the right order? So what happens is there's actually a sequencing number that TCP is responsible for. So once the packet or once the data is received at the end user, there's actually a sequencing number attached to it, and the messages are all sequenced in the correct order. The TCP layer is responsible for this. It's kind of like a label, right? This is packet 1, this is packet 2, this is packet 3, this is packet 4. Put them in this order. Even though the order may not arrive at the same time, once it receives all the information, then it can reassemble the packet, all the different data segments together, put it together to get the long message accurately. So it kind of reassembles at the end based off of the sequencing number. So now let's talk about protocol data units. Going a little more in depth into encapsulation. When we're talking about encapsulation, we usually refer to the OSI model because of the layers are a little more in detail. At each layer, there's a header that's appended to the data. So you have your message. We were going to call that the data. Okay? That data goes up the OSI stack and down the OSI stack at the receiver and at the destination to encapsulate and decapsulate. A sender will always encapsulate, the receiver or the destination will always decapsulate. Okay? What does encapsulation and decapsulation mean? It means that the data, the original message that you want to send over, there needs to be the protocols associated with it to go over the network appropriately so device A and device B can communicate to one another to send that data, that message, with rules of engagement, like we discussed earlier, the correct language, the correct medium, right? That communication channel, that has to all be set up, okay? So what happens is that the sender will take the data, the original data that it wants to send over, an email, let's say. It will encapsulate it. It will add different headers and overhead at each layer, okay? It will add a transport header, a TCP header onto it. So you'll see here, here's the data. I'll add a transport header to it. That's the first level of encapsulation, okay? Every layer, it's called a PDU. The data is called a PDU. But at each layer, it also changes names. So at this transport layer, it's called a segment when you have the data plus a transport header. That's called a segment, okay? That's the transport layer PDU. Now, the data, right? You're encapsulating the data. The sender's encapsulating the data. The sender has to know where the destination is, right? So think about the letter analogy. I have to add the address of the destination of this content, this message I'm sending. So let me add the network header, the destination, append it to this segment or this PDU at the IP layer, and it's called a packet. The packet is a PDU at the IP layer that has the network header, the transport header, and the data. Okay? So we're adding overhead, we're adding additional information so the sender and the destination can talk to one another and receive that data, that email that we're trying to send over. Okay? Then it goes down the layers again, to the next layer. The data link layer. The data link layer PDU is called a frame when it has the frame header, the network header, the transport layer, transport header, the data itself, and then the frame trailer. That's called a frame. Okay? That's at layer 2. So what happens is we add the destination. Now let's add the next hop where it's going to go next, right here. And then after that, it gets encoded at the physical layer into bits, the physical medium that how it's going to go about to transport, to actually deliver the message. So after the frame, it kind of is wrapped up, it's encapsulated, you see here. We go just down the layers, 1, 2, 3, 4, adding additional data, adding additional information of how this data, the rules of engagement, the protocols that's going to be used to send this specific email. All right. And then it gets translated into bits and sent over at the physical layer PDU. Okay. Now, let's jump down into the decapsulation, right? Let's just say we did that and we sent it off to the destination. Now let's talk about decapsulation, right? The bits at the physical layer is sent over to the receiver, right? Let's just say Bob is receiving this email from us. What Bob will do is it will go through each one of these PDUs. So it'll first remove the Ethernet frame. Then it'll remove the destination, the IP frame from it. And then it will decapsulate and remove the TCP frame, TCP segment from it to get to the data. Okay? Once it gets the data, it'll be able to access that email or the website in this case. Hopefully that makes sense. Okay. Now moving on, data access. Okay. So now that we've went over the OSI model and reviewed some of the layers and encapsulation and decapsulation, we're going to mostly focus on addressing. Now, addressing for any data that's sent from one destination to another has two different types of addresses, all right? It has a network layer address, IP address, and then a data link layer address, which is called a MAC address. So any data that's being sent over has two types of different addresses, and for each type it has a source and a destination. So whenever a message is being sent over the network, it has a total of 4 addresses: a source and destination network layer address, and a source and destination data link layer address. Okay? Whenever data is sent, the sender will always add where it came from. Think about the letter, right? You always have who it's being sent from and who you're sending it to, right? So you'll always have your MAC address, which is the data link layer address, and then the source and destination for that. And then also your source and destination layer 3 or network addresses. Okay? Really important to understand that. Now, the data link layer is more of a physical, and then the layer 3 is more of the logical address. Okay? Now, going into the logical address specifically, an IP address is the network layer or layer 3 logical address used to deliver the IP packet from the original source to the final destination. Okay? The source IP address is the IP address of the sending device, which is the original source of the packet. The destination IP address is the IP address of the receiving device, which is the final destination of the packet. This is it sounds rudimentary, but this is very, very important to understand. That the IP address, whenever data is sent from from the source to the destination, the final destination, the IP address never changes. However, the MAC address during that journey to the final destination, the MAC address will always change if there's multiple hops. If it's one-to-one, not really, but something to know is that the final and original source IP addresses will never change. But the MAC or layer 2 addresses will be changing. But let me clarify when I say will be changing. So MAC addresses are directly assigned to physical devices. The physical device has a dedicated MAC address, which is always going to be the same for that specific device. When I say will be changing, is that when data is traveling through the network, it'll go from one device to another device to another device, right? And the source and destination MAC addresses will be changing. The MAC address of the device will not actually change. It's just that flow of information. You know how there's, if we go back to, or here, right, we have our Ethernet frame. We have our IP packet header here as well. The source and destination of the MAC address will change, but the MAC address of the device is always the same. All right. That's not always true for IP addresses. IP addresses can be reassigned, and devices can have utilize the same IP address if it's NATed. Okay. So that's not always true on the other end, but for the most part, MAC addresses are going to be stable, stationary. They don't change. What I'm referring to is when a device original source is sending to a final destination, there's these additional hops. It has to first go to this router, then this router, and then the final destination. Each one of these devices has its own MAC address, and the source and destination MAC address will change in the header, the frame. It'll have different MAC addresses as it's hopping along to the next hop. Okay? But the IP address throughout this whole process, this journey from going from original source to router 1 to router 2 to the final destination, the IP address will never change. The IP address will always be this PC1, and the final destination IP address will always be this web server. But the MAC address along that journey, right, will change. Because these servers all have different sources. I mean, they all have different MAC addresses. Okay. Now, there are times where, for example, if the original source is just trying to talk to router 1, the IP and the MAC addresses will align in terms of I'm sending this data to this IP address, and the IP address has the same MAC address. But in this case, right, when I'm the original source that's sending to the final destination, it's kind of weird. I think we'll get into that in a later chapter. But original source sending to the final destination, it'll have the final destination's IP address, but it'll have the MAC address of the next hop, which is router 1. So what it'll be is original source's IP address, PC1 IP address, PC1 MAC address, and then final destination IP address, router 1 MAC address, because that's the next hop to get to the final destination. Okay, that goes into routing and how data travels across the network. We'll go into that a little later. Okay. So the role of the IP, okay, the network layer address. The role of the network layer address is to be able to route from one network to another network. Okay. So in this instance, let's go back up here. This final destination, 172.16.1.99, is in a different network than 192.168.1.110. In general, you can think of routers being able to move data from one network to another, and switches to be able to move messages and data within that network. Okay? So when it goes to a router, you're pretty much routing it to a different network. When you're sending it to a switch, you can move that data throughout its own environment, its own network, but you can't send it out of the network. Only a router can do it. I mean, that's just general terms. Now there's layer 3 switches, which is a whole, and firewalls that can actually route, but for our sakes, conceptually, let's think about routing. Or routers are going to help us route traffic out to different networks. Switches are going to help us switch and move data around within our network. Okay. Usually each router is going to have its own IP address, separate IP address. Okay. So you see here, these routers right here have different IP addresses, signifying they're in different networks. And then each one of these networks has different devices connected to them that are under its network. The network address is 192.16.1.1. So the router is usually going to have the network address, and then it's also going to have like a subnet with mask, which we'll go into that in a little bit or in a later chapter. which will determine how many hosts it has within that specific network. So router 1 here, we have 192.168.1.1. It can only talk to this switch. These devices can only talk to one another within this specific network, within their own network. If they want to talk to someone outside their network, they need to the router needs to communicate out to router 2. Router 2 is in a different network, 172.16.1.1. As you can see here, router 2, this is the web server's network. The routers have to talk to one another to be able to transmit data. So PC1 can talk to anyone here without actually going up the IP stack, going all the way to layer 3. But if it wants to go outside to the web server, it has to hit its own router. The router needs to talk to the other networks to be able to send that data to the web server. Okay, so that's the role of IP address, to be able to send data outside of your network. Now, the role of the data link layer address. One more thing. IPv4, it's 32 bits, right? 4 octets. I think we went over this already in module 2. But now going into the data link layer, the data link layer address is made of a 48-bit address in hexadecimal. You'll see here, it's 6 hexadecimal number or segments, I guess, that make up 48 bits. The first 24 is the OUI, which is IEEE's assigned block for manufacturers. And then the last 24 bits is unique segment assigned by the brand itself. So for example, if we're talking about Cisco, they will assign these last 24 bits to that specific device. Okay. Now, when the sender and receiver of the IP packet are on different networks, the Ethernet data link frame cannot be sent directly to the destination host because the host is not directly reachable in the network of the sender. The Ethernet frame must be sent to another device as the router or the default gateway. In our example, the default gateway is router 1. R1 has an Ethernet data link address that is on the same network as PC1. This allows PC1 to reach to the router directly. Okay? So PC1 right here, it wants to talk to the web server. All right? I have this message. I want to send it to the web server. But how do I get this message to router 1 to be able to route that message to the next network? So the network can then, or router 2 can push that message down to that web server. I have to have a mechanism of a way to communicate to my router within my network. And we use that Ethernet packet, Ethernet frame, Ethernet MAC address, right? We identify where that the router's MAC address, so we send it to the MAC address, that physical address, so the router can send it out and do its routing. So source MAC address, the Ethernet MAC address of the sending device PC1. The MAC address of the Ethernet interface of PC1 is AAA, and so on. The destination MAC address, when the receiving device, the destination IP address, is on a different network from the sending device, the sending device uses the Ethernet MAC address of the default router or gateway. In this example, it's router 1 is 1111111. All right. Now the Ethernet frame with encapsulated IP packet. So we have the IP packet right here. It's our source, our destination. Okay. Now we take that and we append the data link Ethernet frame header onto it that says, hey, send this PDU to this destination and to this source. Send this message, this encapsulated data to this destination, which is 11111 right here. Then what the router will do is it'll break off this data link Ethernet frame and see, oh, this message is trying to be sent to this destination. And what it will do, it will add its own data link Ethernet header frame. The source will be 11111, and then the destination will be 22222, because that's the next hop. And to conceptualize this a little better is, let's scroll down 378 real quick. So PC1 wants to send a message to the final destination of web server 172.16.199. All right. So what it will do, this is green is layer 2, which is Ethernet. Layer 3 is the IP packet. What it will do, it will take the layer 2 header, the destination and source NIC. So it will have the source MAC address of PC1 and the destination MAC address of the router, okay, in the header. In addition to that, it encapsulated the layer 3 IP packet, the source IP address of the original sender or PC1, and the final destination of the web server, which is 172.16.199. All right. This layer 3 IP packet will never change along the journey. What happens is that it will take this whole PDU, it will send it to router 1. Okay. You see it's green right here. This router, what it will do is remove the layer 2 header and add a new layer 2 header onto it. Okay? The new layer 2 header is going to be the source MAC address of this router itself. In this case, router 1, 11101, and the destination MAC address is going to be this router, which is 2222222. Okay? And that's, you'll see here it's gray. Okay? That's the new L2 header. Now, once this PDU is sent to this router and it receives it, it will remove the layer 2 header. It'll decapsulate. Okay? It will read the L3 IP packet of where the destination IP address is. It says, oh, I need to send it to this web server, this 172.16.199. So what it will do, it will then add a new layer 2 header onto it, its own layer 2 header. The new source MAC address will be its own route, its own. So the source MAC address will now be 22222, and the destination MAC address is going to be the web server's MAC address, which is ABCDEF 1234556. Okay, so do you see how the MAC addresses are changing along the journey per hop? You can see different colors. So what happens is that this PDU is sent to this router. The router will decapsulate it, read layer 3. Okay, this is not me. I need to forward this off to someone else. I'll add my own layer 2, send it. Okay, we sent it. Now, this router, by re-encapsulating it, it will send it to the next router. The next router will decapsulate, remove the layer 2, read the layer 3, say, oh, this is within my network. I know where this is. Let me send it into this final destination. I will re-encapsulate another layer 2 onto it and then send it off with the known MAC address and the source MAC address of mine. Okay? I don't know if, yeah. So you see here, green is for here, router, L2 has its own L2 header, and then the router to server is a blue. Okay? So module 3, we went over a lot. protocols, models, how networking works fundamentally at a high level, how devices talk to one another, the different addresses, encapsulation, protocol suites, stacks, layers, a lot of the fundamentals. This is definitely one of the more important. I know it was very dense, but it's definitely one of the most important. It's the basics. Okay? But that wraps up Module 3. Let me know if you have any questions, and I will see everyone next time. Thanks.